Good. That's great. All right. So obviously, if you change your mind or if something comes up, you have lots of opportunities to ask again. But for today, then, we're going to continue where we left off in section 4. So in section 15.4, we were solving exponential and logarithmic equations. What we're going to do today is we're going to kind of talk about some real-world applications that can be modeled using an exponential or logarithmic equation. So we're going to see situations that come from like chemistry and physics and earth science and like a variety of different places where we have like just kind of natural phenomena that obeys kind of like an exponential or logarithmic pattern there. So there's going to be 4 situations that we're going to look at. So the first one here that we're going to look at is the sound intensity, which we measure in decibels. You've probably heard that term before, whether they're talking about how loud a football stadium is or like a rock concert or whatever. Like that's the measurement that we typically use for how loud something is. So the level of sound intensity in decibels is given by the formula beta equals 10 times log of I over I naught, where the beta is the number of decibels, I is the sound intensity measured in watts per meter squared, and I naught is a constant. It's negative 10 to the negative 12 watts per meter squared. And that just kind of represents the theoretical threshold for human hearing, like what's the quietest sound in theory a human could hear. I say in theory because obviously like different people have a different level of hearing, right? Like if you've been playing rock guitar as a professional musician for 30 years, your hearing is probably shot to all heck, as opposed to somebody that like works in a library all day who's probably has relatively undamaged hearing, or at least has no lifestyle reason to have a damaged hearing. We'll say that. All right, unless they're like riding a motorcycle to work every day or something, who knows? All right, so let's look at an example here. Here it says, given the sound intensity of a busy city traffic is approximately 10 to the negative 5th watts per meter squared, what is the measure of busy city traffic in decibels? So it's asking for something in decibels, so I know I'm going to be using this decibels formula. It asks for the measure in decibels, so I know that we're going to be solving for beta. We're told the sound intensity is about that, so that's my I. And then what's our I naught going to be? Yeah, remember I naught's a constant. So there's that. So we'll just plug that all in. So we got that. And put your calculators away. We can do this with no calculator here. How do I divide 10 to the negative 5th by 10 to the negative 12th? Yeah, you subtract the exponents. Gives me 10 to the 7th. Okay. And then what's log of 10 to the 7th? 7. Why? Yeah, common log is base 10. So log base cancels exponent base. So we just left with 10 times 7 or 70 decibels. What's up? That's supposed to be at 12.
Yeah, that's 6.
Yeah, my penmanship is just like, with 2 arms, it's not great. With 1 arm, it's half as bad. No, half as good.
Twice as bad.
Twice as bad, something. At least it's my left arm that I'm down and not my right arm. If it was that, I just have to cancel class. We can't do it. Just figure it out. All right. Our next example is an earth science one. So we are talking about the Richter scale. What does the Richter scale measure again? Earthquakes, right? Probably most of us knew that from like middle school science class or something. So the Richter scale is designed to register the magnitude of earthquakes. The magnitude of earthquake we represent with the letter R and can be found using the equation R equals log of alpha divided by T plus B, where that alpha is just the amplitude in micrometers. So that's like if this is the ground at normal. When there's an earthquake, the ground's going to be moving up and down, right? So like the distance up or down, respectively, that the ground is moving, that's like your amplitude. T is the period associated with the wave. So the period for this is going to be like the time it takes to go from normal to up to down, back to normal, right? That's like a sine wave. So that's T. T is just that amount of time. And this B is a constant that accounts for the weakening of the wave with increasing distance from the epicenter. So what is this B saying? Well, one of the things about trying to measure an earthquake is predicting where and when an earthquake is going to happen is actually really difficult. Right? Kind of impossible. So you just have to measure your earthquake with wherever your instrumentation is when it happens. And we know kind of inherently that like the further you get away from the center of an earthquake, like the less intense it feels, right? So this B is like a correction factor. Okay, like I measured, like this amplitude in this period, but I was like 55 miles away from the earthquake. If it was actually, this measurement was done at the epicenter, like I'd have to add something else to that to account for like the distance I am away, right? So these values for B are something that was computed in advance, like empirically. They're going to look at data that they've collected and like model something, and it's just something you'd like look up out of a table or something. Okay, my sensor was 19 miles away, so I'm going to add 4 to it or something. It'd be something like that. So that's all this B is. So it's just like, it's like a function of how far away you are from the center of the earthquake, or the epicenter, we'd call it. Everybody cool with that so far about what the letters mean? Okay. Let's look at an example. Drop that in. So this says the infamous San Francisco earthquake had a Richter scale magnitude of 7.5. How many times more severe, that's a tough sentence to read, was the most severe earthquake ever recorded, the 1960 Chilean earthquake that had a Richter scale magnitude of 9.5. Well, you read that, and it's really kind of, doesn't seem like there's enough information here, right? At least at first glance. And even what is it asking for is maybe not entirely clear. So what it's asking for is like what is the ratio of the vertical displacements, the amplitudes of the two earthquakes, right? It's asking how many more times severe. So like the up and downness is the stuff that really makes an earthquake bad. Everybody's cool with that so far? So that's what we're going to be searching for. And we're given two earthquakes. So really we have like two sets of these, or two different equations, right? With two different sets of parameters. So I'm going to just add a subscript to each of the variables there to indicate whether it's belongs to the first earthquake, the San Francisco earthquake or the Chilean earthquake. All right. Now all we know is R1 and R2, correct? So somehow we're going to have to get rid of some of this other stuff. So let's think about what these terms mean again. So the B's are a correction factor, right? So if I'm measuring something from far away, it's like add that on after my measurement to like make it look like it was already, or that the measurement was done at the epicenter, right? Now, I'm given Richter scale magnitudes, which means that was already like that correction factor is already done. So that's like 7.5 at the epicenter, or 9.5 at the epicenter, right? So what does that mean for the B's in this situation? They're just zero, right? Yeah. So we can just forget about the B's. So, all right, well, that's something. I guess I'm just going to think about this as a system of two equations. And since I want to compare the strong one to the weaker one, I'm going to do like equation 1 minus equation 2. Now, R2 is 9.5 and R1 is 7.5, so that's just going to be 2. And if I look above, I notice what I have is a difference of two logarithms, right? So I can apply the quotient properties for logarithms. Oh, boy, Mr. Kulik. Okay. And I can write that. Since it's divided, I multiply by the reciprocal, right? Rather than writing a fraction on top of a fraction, which yucca-rooskies, I don't like the look of that. This seems a little bit nicer. Okay. But I still have this getting closer, right? Because I can see the alpha 2 over alpha 1 now, which is what I'm looking for. But I have this stupid T1 over T2. So I think I'll just like product property that piece out. And now let's think again, what are these T's representing? So it's like the period, like how long it takes to do like the Earth to move up, move down, and then back to the starting point, right? Do you think that's going to be a big number or a small number?
Small.
Probably really small, right? Because it's, earthquake things are moving up and down really fast. Like that's probably the case, right? And do you think there's going to be a big difference between whether it's moving a big distance or a smaller distance? Probably not much difference, right? Like it's going to be real fast either way. Anybody ever felt an earthquake before? Just as an aside.
Really? Where was it? Was it here?
It was, so like, I don't know, it was like like 15 years ago or something, there was an earthquake in like eastern Illinois, and I was living in southwest Michigan, and you could kind of feel it. Like it was in the morning, I was still in bed or whatever, and it's like, felt like the house shake for just a second. It was very slight. It was a pretty weak earthquake. It was like a 4 or 5 magnitude earthquake in Illinois, and I was, like whatever miles away. But like, thought it was weird. Heard on the radio like later that day that there was an earthquake in eastern Illinois. I was like, I bet that's what that was. So it's very like, almost like if you're in a, like an old house and someone's like jumping up on the bed on the second floor and you can feel the house kind of moving or something, kind of like that. It's very subtle, but like felt it. It was an earthquake. It was a nothing burger, but it's kind of, the best case scenario for saying that like, oh yeah, I've been in an earthquake before. Anyways, so the point of the matter is if T1 and T2 are going to be very close to the same number, right? If I take two things that are almost the same and I divide them, what do I get? Basically.
1.
1. Great. What's the log of 1?
10.
No.
-0.
0. Yeah, so guess what this does?
It goes away.
Just goes away. So we'll just say 2 is about just this. So then we can just cancel out the log by doing exponent base 10 to both sides. So 10 squared is 100. And there we go. That the Chilean earthquake was 100 times as severe as that San Francisco earthquake. Ay caramba. Glad I wasn't in that part of Chile in 1960. At least on that day. It was probably a lovely vacation destination otherwise. Other than the earthquakes. The next question is a chemistry situation. So those of you that are in chemistry, have taken chemistry, probably recognize pH.
I know this one too.
That's amazing. All right, so pH is the relative acidity of a water-based solution. So the measurement is based on the concentration of hydrogen ions. So that's the bracket with H+. When you put an element in a bracket like that, it's talking about the concentration of it. And typically we measure that concentration in moles per liter. Chemistry people, what's that called? Moles per liter?
Molarity.
Molarity, good job. So again, pHs go from 0 to 14. 0 is the most acidic. 14 is the most basic. 7 is considered neutral. That's the pH of like deionized water, like pure water, pure H2O with nothing else kind of like floating around inside of it. So that's the gist of that. Let's look at an example. Here it says a really sour lemon is found to have a pH of 2.2. And a bottle of bleach is found to have, oh my God, what are we doing here? Found to have a pH of 10.2. And we're asked, what is the hydrogen ion concentration of the two items? Okay, well, I have a pH, so I'll just plug that into the old pH formula. And we'll just solve for that concentration of H2 or H+. What is the first thing I'd want to do to solve for that?
Just take the 10
Not yet.
Oh, divide by -1.
Yeah, you gotta get that negative out of there. So divide by -1 or multiply by -1, either is okay. And then we can use exponent base 10, as Joe was starting to say when I said not yet. And the capital letter M is our abbreviation for molarity. I think it's actually like a, like a script M, right? Like that or something. But good enough for us. We'll just use a capital.
So would we not simplify like -2 times 2?
That's -2.2.
Oh,
So no, I'm not going to simplify that because it's already simplified. It's just my bad penmanship that looks like.
that's all right.
That's okay. I get it. Don't sig fig me. All right. So to do the bleach, same thing, right? I'm just going to skip the algebra because it's the exact same algebra. Is that cool with everybody? Yeah, I thought it would be. All right, and part B says how many times greater is the hydrogen ion concentration of the bleach than that of the lemon? That's clearly some kind of typo because the lemon is the acid, so that should definitely have more hydrogen ions than the base. So here we're just going to look at the ratio. Which again, I can do that with no calculator. I'll just simplify. So that that lemon is 100 million times the concentration of hydrogen ions is the bleach. Whoa! That's a lot of hydrogen ions. All right, and our last example situation before we move on to the next stuff is kind of like another physics-y one or chemistry, depending on where you call it thermodynamics. Yes, sir. Absolutely. So this is about Newton's law of cooling. Refers to the fact that objects that have been heated will cool to the temperature of their surrounding mediums. So like, if you cook something in the oven, you take it out and you let it cool, eventually it'll be the temperature of the room that you're cooling it in, right? Or if you're like a medieval blacksmith and you're like forging a sword and you like dunk it in the cold water to part of your annealing process. So like the surroundings would be the water. Anyways, to model this equation, to model this cooling, we use the equation T of T equals T sub m plus T naught minus Tm times e to the negative kt, where T of T is the temperature at some time T. Tm is the surroundings temperature. T naught is the initial temperature of the heated object. K is a constant specific for the given substance. And then T is the time elapsed or whatever. The K, again, specific for the given substance, right? We've seen that some things cool off faster than others. Like you cook up some of those pizza rolls and those things are like molten lava for like an hour. You go to McDonald's and you bring your fries home. By the time you get 5-minute drive, your fries are cold, right? Stuff just cools at a different rate. It'll be specific to the substance, right? Whether you have molten lava pizza rolls or you have, like your cold French fries. Let's look at an example here and go about doing this. Here it says a hard-boiled egg is heated to 96 degrees Celsius and then placed in a pot of 16-degree water to cool. After 4 minutes, the temperature of the eggs is 45 degrees Celsius. find how long it will take in total to cool the egg to a temperature of 20 degrees Celsius. So hopefully it's pretty obvious by reading the question that we're talking about stuff cooling off. In this case, it's some eggs that we're boiling. So we're going to be using that Newton's law of cooling. Oh, thank you. There we go. All right. So what is the 96? This is the hardest part, is getting the stuff in the right place.
Temperature. Do it in Celsius.
T and
It's TF. No, it's TL.
It's the initial temperature of the object. The eggs are what are cooling off, right? We boiled them. Yes, and again, FYI on this, the units don't matter as long as the units are all the same, right? So if everything is in Fahrenheit or Celsius or Kelvin or whatever, as long as it's all the same temperatures, you're fine. Okay. What is the 16 degrees then? Good, because that's the water that we're going to dump the eggs into after we're done boiling them. Okay. It says after 4 minutes, the temperature of the egg is 45 degrees. What does that mean?
That's the cool
That means that T of 4 would be 45 degrees, right? Everybody's cool with that? And then it asks, how long will it take to cool the egg to a temperature of 20 degrees?
So are we just calling 45 for 5K?
So that's exactly right. So this is going to be 2 steps, because you notice that the thing we're not given any information about is the K. So yes, dead on. Everybody's cool? Okay, so starting off, we have 45 equals 16 plus 96 minus 16, e to the negative k times 4. To solve for k, first step should be?
Subtract 16.
Okay. At the same time, I'm going to simplify. Yep. Yes, sir. Natural log of both sides. And then just divide by 4. And again, I'm going to write it as times negative 1/4. Just so I don't get confused looking back at whether I'm dividing that negative 4 inside the logarithm or outside the logarithm. Here it's clear that it's like happening outside. Oops. All right, so I have negative 1/4 times natural log of 29 over 80. So that's about 254. But this is going to be, these problems are going to be kind of sensitive to rounding. So what I'm going to do is I'm going to store this value as the letter K, so I can just use that later on. So I don't have to remember all the decimal points. I don't have to really settle for ending rounding. But I'll write that down. Now I'm able to solve the problem that I'm really interested in. Just for the record, I'm just going to write K, even though we know what K is now. Everybody's good with that? I just don't want to write all the decimals. It's just like a hassle for me. So same steps, right? I'll subtract the 16, simplify, divide by 80. Yes, I know that can reduce, but it's all going into the calculator anyway, so like, who gives a rip? I'm not gonna hassle with it. Natural log both sides. And then divide by negative k. That ought to do it. So negative 1 divided by k times the natural log of 4 divided by 80. Oops. Divided by 80. And I have 11.8 minutes. What if I wanted to write that in minutes and seconds? How many seconds is 0.8 of a minute?
Like 40. No, 48. Like 40.
So I just take that decimal and multiply it by 60, right?
I just put it.
That's all good enough for government work. Now, again, the question here just said how long. So it doesn't really matter how you represented it, but if it asked for like in minutes and seconds, I just wanted to like just take a second and talk about how to do that. Because it should be pretty easy. It's just one of those that like unless you think about it for a minute, it's like, how do I do that? All right. Now on to section 5.5. In 5.5, we're going to talk about financial mathematics. Ooh. The main topic we're going to start with is talking about interest. And we're going to start with the most basic situation, really the dumbest situation that nobody uses, but that's called simple interest. In simple interest, the only thing that's going to earn interest on your investment is your initial. So in year 1, you earn like 5% of whatever you start with. In year 2, you just earn 5% of whatever it was you start with. The amount of interest paid every year is exactly the same because it's just based on that initial investment. So the variables here, FV is the future value. That's the account's value in the future. PV is present value. That's the account's initial value, the principal that you invested. Little r is the interest rate written as a percentage. And N is the number of years, the length of your investment. So looking at that real quick here. So here's an example. Says if you invest 6% or invest $2,000 at a 6%, and it should probably say simple, interest rate, how much total money do you have in the account after 3 years? So again, we see simple interest, so we're going to use the simple interest formula. We're looking for future value. The present value is 2,000. The R is 6. The N is 3. And when I punch that all through my calculator, I get 2,360. Everybody's okay with that? How much interest did I earn?
$360.
Great. Yeah, so you just take the future value and you minus the present value, and the difference there would be the amount of interest that we earn. Cool. Again, simple interest, real dumb. Nobody uses this. It's just kind of like a starting point. The next kind of situation we'll talk about is compound interest. And this is a situation where you earn interest on the total value of your account at the end of each year. So at the end of year 1, you earn interest on the principal. At the end of year 2, you earn interest on the principal and the interest you earned in year 1. At the end of year 3, you earn interest on the principal. You earn interest on the interest you earned in year 1 and the interest you earned in year 2. And it goes on and on like that, right? So here we picked up a new letter, FV and PV, still future value, present value, R still interest rate, N still time in years. K is the number of compounds per year. And now almost always in our problems, that's going to be hidden for us and not written out as a number, but rather in a word. So if we say annually, that means that K is 1. Semi-annually, K is 2. Quarterly, K is 4. Monthly, K is 12. Weekly, K is 52. 52 weeks in a year. And change, but we're not going to worry about the change. And then daily is 365 and change. We're not going to worry about the change, though, right? Like there's a leap year every once in a while because there's leftover hours at the end of each year. But like, we don't give a rip about that. All right, so let's take a look here. If you invest $2,000 at a 6% interest rate compounded annually, how much total money do you have in the account after 3 years? Notice that this is the exact same problem, except it says compounded annually. So we know immediately that we're going to be using the compound interest formula. So PV is still 2,000, R is still 6. What's the K going to be in this case? 1. How did you get 1? Annually. So when I go ahead and plug that through in my calculator, I get about $2,382.03. Why did I round that to the hundredths place?
That's how money is measured.
Yeah, money is measured up to the penny. So if it's a money problem, always rounding to 2 decimal places, right? So how much interest did we earn here? Yeah, so what's the how much is the difference between the simple interest and the compound interest? Like $22, right?
Yeah.
Is that a big deal?
It's more money.
It's not so much a big deal right now. But what if instead of doing this for 3 years, we did it for 100 years?
Big, huge, exponential.
Oh, you're funny, guys. It's not what I wanted it to do at all. So if I do that, simple interest, after 100 years, I got 14 grand. Okay, that's pretty cool. That's a lot of money. If I do this on compound interest, I have $678,604.17. Now all of a sudden, it's a big difference, right? In fact, it's probably not hard to imagine that there were multiple years here where we earned more than $14,000 just in interest, right? Pretty likely that that was the case. Now it's a big deal, right? The takeaway, in the short term, simple interest versus compound interest, not a big deal. Over the long term, massive deal, like orders of magnitude deal, right? Okay. The next question would be, okay, so we have this like differing numbers of compounds per year. Like, how big of a difference does this make? Suppose I have some situation, I look at how much my investment changes if I change the amount or the frequency of the compounding, right? So I'm just going to do all of this problem on my calculator because it's like super repetitive to write down. And the takeaway is going to be not so exciting. But it's worth doing. So here's compounded annually. Okay. If I change this to semi-annually, how much of a difference do you think this is going to make? Like a $1 difference, a $10 difference, a $100 difference, a $1,000 difference?
300,000.
Okay, let's look.
502.
$6.
Darn.
That's not that big of a difference. Okay, so doubling the number of compounds, I went up by $6, right? What if I go from 2 to 4? I double it again. Do you think it's going to be?
It's like 40 bucks.
12.
40 bucks.
Look, it's $3.
It's less.
Well, it's still more than the original. It's like now $9 more than the original, but like less of an increase. Exactly. What if we go to monthly? So this time it's a 3-fold increase.
40. It's going to be
$13.
Let's see. A little less than $3. Okay. Well, let's go to weekly here. That's 52. That's like over 4. Oh, Boise. That's like over 4 times as much.
1.83.
Less than $1. Well, let's go to 365. That's like a 5-fold increase now. Or I'm sorry, like a 7-fold increase. That's got to be something huge, right? Yeah, it's like 30 cents. Man. So what is our takeaway here?
At a lower rate.
Yeah, like more compounds is better, but it's not that big of a deal, right? You'd much rather have a better interest rate or longer time period or something like that, right? So the more compounds, it's better still, but it's like we're not getting excited. Ooh, I got weekly instead of monthly. Okay, that's good, but like, don't like throw yourself a party about it, you know? All right, let's look at some compound interest situations here. So Mara has $1,000 and places it in a savings account with 6% annual interest compounded monthly. How long will it take before Mara has $4,000? So again, compound interest. So future value is 4,000, present value is 1,000. R is 6. What's K? 12, because it said monthly. Good. So we're going to be solving this equation, right? How do I solve this equation? What do I want to do first? Divide by 1,000. Great. At the same time, I'm going to simplify that stuff inside the parentheses. Is that okay to you guys?
Yeah.
Okay. So I just typed that into my calculator. I just did it in my head, though. All right. What's next? Excellent. Log base 1.005 to both sides. And then we'll just divide by 1 over 12. Or I'm sorry, divide by 12 or multiply by 1 over 12. And when I type that all into my calculator, I get about 23.16 years. Just as a reminder, how do I type in something like log of 1.005 into my calculator. Math. Go to the bottom, find that log base command, and type in any base you want now. Boom. Everybody cool? Remember the log base command? Super helpful. All right, let's look at another compound interest situation. Here we're told that Gwen is gonna put $600 in a savings account. What annual interest rate would she need if it's compounded weekly if she wants to have exactly $1,500 in 10 years? Well, that $1,500 is our future value. Our present value is the 600. The R is going to be our variable. The K is, what's the K? Nope. 52.
My bad.
It's okay.
Gosh.
You got confused between N and K. Okay. Everybody cool with how we filled in? Okay. Solving for R, what's my first step? Divide by 600. I'm going to reduce that a little bit. Yes, I know 15 and 6 can reduce, but like, I don't care. I just wanted to do the part that was like, I can't screw up in my head. If you wanted to reduce more, you could, or not at all. That's fine. It's all going to go in the calculator eventually anyways. What's up next? How am I going to get rid of that exponent of 520? No, I can't take a log with a variable in the base. Oh, you can't distribute exponents.
And you're going to split it up.
No, man.
Oh.
Bad news.
I'm suggesting anything, Joe.
What if I had like just x to the 520 equals, you know, this? What would you do there?
I would take the 520 through.
Exactly right. Let's do the same thing here.
Wait, actually?
Yeah.
What?
That's exactly the right thing to do. And then we'll just subtract 1 and multiply by 5,200 then, right? So go to my calculator now because I can't do that stuff in my head. So I have 5,200 times -1 plus, and to type in a 520th root, I'm going to type 520 and then press the math button and choose option 5. Look at that. Then I'll have to do 15 over 6 and close my parenthesis. So I get about 9.17%. Everybody cool? Okay. Let's see here. Next thing we're going to talk about is we're going to talk about continuously compounding interest. If I say interest is compounded continually, how many times is that happening per year? What would the K be?
2,
More. More.
3,
More.
5,
More.
6.
Infinity.
Oh.
That is right. So what is that going to do to our compound interest formula? Because I can't exactly plug infinity in here, right? So we're going to have to do a little bit of work here. So let's think for a moment. I'm going to say let x equal 100k over r. Let's do that.
So we have r over 100k.
Yep. So that's going to mean we have a 1 over x in here. Everybody agree? And the numerator, I have nk. I'm going to multiply that by 100r over 100r so that I can rearrange that numerator to be 100k over r times rn over 100. Everybody's okay with that? And we said that 100k over r is just x, right? And the exponent, a product of two exponents is the exponent of the exponent, right? Notice that I no longer have any k's, correct? So as k goes to infinity, what's happening to x?
X.
Right? Exactly. And if I take this, I should recognize this, because I know that the limit as x goes to infinity of 1 plus 1 over x to the x is equal to this is a definition. We did it just like, nope. We did it like a week ago.
Oh.
That's just E. It is. So what do we have then? So there's our continuously compounded interest formula. Do-do-do-do! Ta-da!
We're done.
Do you want to be done? Okay, we can stop here.
No, there's more. Keep going.
I mean, we need another day to finish anyways. Whether we stop here and do more the next day or do less, it doesn't matter to me.
Just do whatever you're gonna do.
If you guys, this is about where I would have stopped. This is fine. Yes. So we'll stop here. That's fine. At this point, you guys can do up to 150. That won't be due until next weekend, though, the 28th.